So second law, so far we have discussed all the statements we have made so far invariably refer to as cycle. So the two statements of the second law which we mentioned and then showed that the two are equivalent, they say for a for something operating in a cycle. Again, the Carnot cycle, everything was discussed in the context of a cycle. So if you look back, first law also, we first, when we made the statement, we said cyclic integral of Q and cyclic integral of W have to be the same. Now, in the case of first law, after making that statement, we showed that if we take all different paths, but all starting from the same initial point to the same final point, in that case, the first law implies that there will be a function called energy, which is a function of the state of the system. So similarly, we have made a statement for the second law in terms of a cycle, but from that we should be able to define a certain thermodynamic property which follows from the statements of the second law. So that quantity will be the entropy. So in order to define entropy, we first need to discuss the inequality of Clausius. It states that for any cycle, reversible or irreversible, the cyclic integral of delta Q by T is less than or equal to 0. It applies to both heat engines and refrigerators. Now the book makes a statement which it doesn't explain. It says that any reversible cycle can be represented by a series of Carnot cycles. So therefore, we need to prove this statement only for Carnot cycles. So there it doesn't explain further, but some of the books, they say that if you have a certain cycle, then if these are isotherms and these are adiabatic, then this entire cycle, which was arbitrary, not a Carnot cycle, can be considered as a superposition of a number of Carnot cycles. So then it says that if we can prove this for Carnot cycles, both heat engines and refrigerators, then from this statement that any cycle, any reversible cycle can be represented as a series of Carnot cycles, then since it applies to every individual Carnot cycle, it should apply to the superposition also. So then it says that if we can prove it for heat engines and refrigerators, then that should prove our Clausius inequality. So in a cycle, what is the value of this integral? So that is what the Clausius inequality says, that in a cycle, over the entire cycle, if you calculate delta Q by T, that should turn out to be less than or equal to 0. So delta Q by definition is delta Q added transferred to the system. So therefore, any Q rejected is counted as negative. So that is why, otherwise if everything were positive, this could never be negative. So that convention has to be kept in mind. So then, if this is a Carnot cycle, so we are assuming that any arbitrary cycle can be represented as a series of Carnot cycles. So let's consider one Carnot cycle. So for a Carnot cycle, if you recollect the definition, there were 4 reversible processes which together constitute a Carnot cycle. So then the 4 processes were 2 isothermal processes and 2 adiabatic processes. Adiabatic means delta Q is 0. So the adiabatic processes do not contribute to this integral. The only ones which contribute to this integral are the isothermal processes. So if you remember, we said that if you consider a working substance in the engine uses a certain working substance to which, so it might be a fluid inside a cylinder with a piston. So you transfer Q to it, it rejects Q, and it does some work on the piston. So then, if you consider the engine, that engine, if it has a working fluid which undergoes phase change, then QH and QL can be added while the system does not undergo any change in temperature. because during phase change, the latent heat is supplied, so there is a transfer of Q, but there is no change in temperature. So such a process could be part of the Carnot cycle. So then the heat addition to the working fluid is QH, and that occurs at temperature TH. This Q is transferred to the working fluid. So for the system, this Q is positive. And there's one more isothermal process during which Q is transferred. That is the QL rejected to the lower temperature reservoir. Now, if I consider the system, the heat engine to be the system, in that case, the Q is negative because Q by convention is positive if it is transferred to the system. So if it is transferred from the system, then it's negative. So by definition of the thermodynamic scale, so QL by QH had to be some function of L by some function of H, and that we chose to be linear, in which case the Carnot efficiency came out to be 1 minus TL by TH, and then we showed that if we take the ideal gas temperature scale, where the ideal gas temperature is proportional to the pressure at constant volume in the limit pressure being very low. So that is the definition of the thermodynamic of the ideal gas temperature scale. So if we define that as the temperature and then calculate a Carnot for a Carnot cycle which uses an ideal gas as the working fluid, in that case, the Carnot efficiency again turns out to be 1 minus TL by TH. So therefore, this definition of the thermodynamic temperature scale becomes identical to the ideal gas temperature scale. So from this definition of the thermodynamic temperature scale, we have this, which implies so then in this case is equal to 0 for a reversible. What if it is irreversible? If it is irreversible, if I have the same value of QH, the irreversible cycle has a lower value of W. If it has a lower value of W, the QL value is higher. if QL is higher, so for the irreversible engine, keeping TH and TL same and QH same, I get higher QL. So therefore, these are all same. This is higher. So the negative term is larger. So therefore, for an irreversible cycle, now for a refrigerator again, by the same logic, uh, Carnot refrigerator is actually a reversed Carnot engine. So again, this ratio applies, and for a reversible refrigerator, again you'll have equal to 0. And for an irreversible refrigerator, I'll leave it as an exercise to you. Demonstrate that this will be less than 0. Now, from this Clausius inequality, we'll now see how we can derive the property called entropy. So let's say I have two thermodynamic states. So I'm assuming this is one pure substance in one phase. So there are two independent thermodynamic coordinates which specify the thermodynamic state of the system. So on this thermodynamic coordinate space, let me choose 2 points 1 and 2, and let me have one path from 1 to 2 by A, a return by a path B, and an alternative path from 1 to A by C. Let us say all of these are reversible processes. So we had found that Clausius inequality says this is less than or equal to 0. It is equal to 0 for a reversible and less than 0 for an irreversible process. That is what we found for the Carnot cycle, and that holds in general. So if all these processes are reversible, in that case, so a cycle is a process which brings back the system to its original state. So if one possible cycle is I go from 1 to 2 by path A and return by path B. So since both processes are reversible, here we have the equality. An alternative is 1 to 2 So I'm going along C and returning along B. Again, it's a reversible cycle. So therefore, the Clausius inequality again, since it's reversible, becomes the equality applies, and I have this. So now A and C are any arbitrary reversible paths between 1 and 2. So this means if it's equal for any arbitrary path, now I could have chosen them in any way. So therefore, integral of delta q by t from 1 to 2 has to be the same for any path connecting 1 and 2. So then, regardless of what path I choose, as long as it's a reversible process, this integral has to have the same value. So then I can use this to define a certain property. So that property we call S. So then if I arbitrarily choose a value for a certain point, say point 1, I choose S1 to have a certain value. Then if I go from 1 to 2, this integral is the same. So I can define this integral from 1 to 2 as the difference between the property at 1 and the property at 2. Now this requires the equality, so therefore it has to be a reversible process. So this quantity S is called the entropy. So if I have a system in a certain thermodynamic state 1, and I take it by any reversible process from state 1 to state 2, then during the process, if I integrate delta q by t from 1 to 2 along the reversible process, that should give me by how much entropy has changed from state 1 to state 2, which is stated in this relation. Okay, before I proceed further, just a question. Do any of you have any unresolved questions, something which you think need to be discussed before the class test? Because if that is so, we have only today's class and tomorrow's class. So in case there's something which is still not clear, we could discuss it now. Okay, regarding the manner of conducting the exam, I think since I'm doing it in a slightly different way, let me mention that also, that you should be prepared with blank paper enough to write a 1.5 hour exam. So you'll write it with pen and paper. You'll be the question paper will have clear instructions on what you have to, what are the final answers you have to upload. So that has to be uploaded within the time limit specified, and you get an additional 10 minutes. During that 10 minutes, you have to scan your full answer and email it to me. So then um, for that purpose, some arrangement so that you can scan your answer script, that also you have to keep it ready. So it could be a cell phone camera or whatever. So you have to scan and email the full answer script to me. Now, for the file names, actually the final answers, which will be a short answer, just the final answer. So those could be included in the email, but then I have to preserve all the emails. What I would suggest, that if you send that as a text file, as an attachment, then I could download all the text files and keep those in a folder. Now, the whole process of checking that becomes easier if those are arranged sequentially. So then I would suggest that for your files, so the final answer, that file you name it as roll number.txt. So if your roll number is 20XX, then this could be the file name. And the full answer script this could be JPG, PDF, whatever. So this would be okay. So I'll include this in the instruction in the question paper. So if you send me the full answer as an attachment, as a text file with this name, and the full answer script scanned with this name, then it will be easy for me to process all the files. Okay, so from the Clausius inequality, assuming that all processes are reversible, we derived a property called entropy. So if I have a point 1 and I arbitrarily, so if I choose a certain point, and so this is somewhat like potential, that this integral from from one point to another, this integral gives you the difference between the property from one point to the next. So this is somewhat like a potential difference. Now, if you look back, the statement which was made regarding a potential, so whether it be gravitational potential or electrostatic potential, it was always stated that the physical quantities are always in terms of differences or gradients of the potential. So therefore, the absolute value of the potential is undefined. So we can choose the potential to have a certain value at one point. Once we have specified it at one point, then potential differences are physical quantities. So then it gets defined at all other points. So similarly, if I say that entropy, I choose it to have a certain value at a point 1. I choose any one point, call it 1, and choose the entropy. I could choose it to be any value. Now, what it will be, that again gets specified by the third law of thermodynamics, but at the moment we are not discussing that. So at the moment, we are free to choose the value of entropy at any one point. So then, if I want entropy at any other point, I take any arbitrary path connecting 1 and 2, evaluate the integral of delta q by t, which we have shown that from Clausius inequality, assuming that the path is reversible, it will be independent of path. So any path between 1 and 2, that integral has to be the same. So that I take to be the difference between the property and entropy from point 1 to point 2. So I use this integral to define what is S at point 2. Now if I have another point 3, I choose again any arbitrary path from 1 to 3 to define the entropy at point 3. Now, from our definition of entropy, this applies to any reversible path between any 2 points. So then, I have defined S2 as Now the question is that I also must have so if I define S2 in this manner, S3 in this manner, will it satisfy this? So I'll leave this as an exercise to you. Using the Clausius inequality and the statement that the equality holds if the cycle is reversible, prove that if S2 is defined in this way and S3 is defined in this way, then S3 minus S2 will also satisfy this. So if I connect these by a these 2 points by a reversible cycle and calculate this integral, this should give me a value which is consistent with these two. So prove this from the Clausius inequality. So let us say we have two different cycles. One is from 1 to 2 by a reversible process and back from 2 to 1 by a reversible process. So the entire cycle is reversible. And the other cycle is from 1 to 2 by an irreversible process. An irreversible process is denoted by a dotted line because the irreversible process, it's not in a thermodynamic equilibrium during the process. So there are non-equilibrium, it's a non-equilibrium situation. So therefore, we don't know the thermodynamic state at intermediate points. So therefore, thermodynamic state is defined for an equilibrium state. If it passes through non-equilibrium states, we denote it by a dotted line. So then 1 to 2 by C and back from 2 to 1 by B, the entire process is not reversible, it's irreversible because this part is irreversible. Now we have shown for a Carnot heat engine that an irreversible engine, for an irreversible engine, the integral of delta Q by T is negative. So QL was larger, so that gave us from that we saw that integral of delta Q by T for an irreversible Carnot engine is negative. Now, taking the argument that any irreversible cycle can again be expressed as a a superposition of Carnot-like of um, cycles with isothermals and adiabatics. So then uh, any irreversible cycle would also have that property that integral of delta Q by T would be negative. So the Clausius inequality tells if you want to apply it, if the entire cycle is irreversible, then integral of delta Q by T is less than 0. So then for the reversible cycle, let me deduct the first equality from the second inequality. So this is equal to 0. So I can deduct this from the left hand side. Since it is 0, it will not change the inequality. So then what I get is this. Now C was an irreversible process and A was a reversible process. This was the definition of entropy. Sorry, this would be less. So the delta Q by T from the same point 1 to 2, if I calculate for the irreversible process, it is smaller. So therefore, So if it's a small infinitesimal path, this applies. So I'm assuming that it's between the same two endpoints. So then for the infinitesimal path, ds is equal to so if I calculate delta q by t for an irreversible path that has a smaller value, so S, if I go by any reversible path, that gives me a certain change in the property S of the system. So I use this to define entropy of the system. So this defines entropy as a function of the thermodynamic coordinates. So once I use this definition for entropy, this uniquely defines entropy at for any thermodynamic state. So then if I have a gas and I specify what is the, so if I have say steam and I specify the pressure and the temperature, this definition tells me what is the entropy, provided I have defined entropy at a certain point. So once I've defined at one certain point, I can use this relation to define an entropy everywhere. Now if I go from the same point, from a point 1 to a point 2, the delta q by t for an irreversible will turn out to be less than for a reversible. So then, since I'm going again from point 1 to point 2, my change in s is the same, but this integral of delta q by t is less. So then I add a certain delta s, which is the s generated in an irreversible process, in order to make this equal, because this quantity depends on the endpoints. This integral, so this quantity depends on whether it's reversible or irreversible. For irreversible, it is less. So therefore, since ds is specified once the endpoints are known, if this quantity is less, I must add a certain delta s generation in order to this quantity in order to get ds. So this is the definition of entropy. Okay, there's not much time left, so I think, how do you calculate entropy change for certain substances, be it solids, liquids, or gases, or ideal gases? We'll take up that first, so you get a slightly more direct idea of how to calculate entropy, and then we'll discuss further how to write the entropy balance for a control mass and for a control volume. So it is this which defines the entropy. If you have any questions, you can ask.
Sir, a question regarding the exam.
Huh.
Sir, whatever you taught today will not come in this Friday's test, no? Means,
No, today's part will not be included.
okay, sir.
When
Thank you,
we,
sir.
So how many questions will be there?
there'll be 3 questions, but not of equal weightage. So this is like the conventional exams that in the conventional exams, typically we used to set long questions which would on the average take around half an hour each. So if it's half an hour each, 1.5 hour exam, you would have 3 questions. So that is how I've designed it. But the 3 questions do not carry equal weightage. So the time required also is half an hour on the average, but in actual fact, it will not be half an hour each. Some will require less than half an hour, some will require more than half an hour. So it's like the conventional exams that you have long problems. So nowadays, long problems you would have probably have encountered in your high school and higher secondary exams. So it is on that pattern.
Okay, sir.
Okay, if there are no more questions, we'll close here.